So in the last video, we learned about centripetal and centrifugal forces, and in this video, we're going to derive the equation for centripetal acceleration. Okay, so I'm going to start off by drawing a circle. Try to make this as big as possible. Alright, and so we've got, let's say we've got some particle moving counterclockwise in a circular motion. Alright. So identify a couple of things here. So here's an angle. These are the radii, they're equal, right? And let's say that I'm looking for the acceleration through from this point to this point. Okay. So I know that the velocity vector is tangent to the circle and looks something like this. Let's call this V1. Here's my other one, V2. It's supposed to be tangent. Okay. And I know that they are equal in magnitude. The particle is traveling at a constant speed around the circle, but not constant velocity because it's changing direction. So the magnitude, or the length of V1 and V2 are equal, but their directions are different. Okay. So we have learned that acceleration is equal to delta V over delta T. And we know that delta V is equal to V2 minus V1 over delta T. And just to make a point, I can rewrite this as V2 plus negative V1 over delta T. Okay, so I know that this top part right here is delta V. Alright, so I want to graphically show you what delta V would look like. Okay, so first let's think about what negative V1 looks like. So here's V1. Negative V1 is essentially V1 just flipped. So same magnitude, just flipped 180 degrees. So it looks like this. That's negative V1 in green. Okay. Now, when I add two vectors, what I do is I take this vector and place its tip, the arrow, on the end, the tail end of the second vector. So I'm just going to, if I could copy and paste negative V1 and just directly place it right there. So same direction, same magnitude, just shifting it down. So I'm going to do my best to draw this as accurately as possible. So it's going to look something like that, let's say. This is negative V1. And the result, the addition of these two vectors gives me, remember, delta V. So remember that V2 plus negative V1 gives me delta V, and that's this vector. So this is delta V. Okay. Remember that V2, V1, and negative V1 all have the same magnitude. So the length of these vectors are all the same, they just have different directions. Okay. The next thing to consider is we know that this distance around the circle is delta x. So this is how far the particle has traveled. I'm going to draw in a chord. And a chord is just a straight line that connects two points on a circle. So it looks something like this. Draw it in a different color, actually. Okay, so that's the chord. And as the angle theta, this angle here, becomes smaller, the length of this chord gets closer and closer and closer to this arc length, the actual path of the particle. Remember that this arc length is delta x. So what I'm going to say is that, just for the sake of this problem, that theta is very, very small, and we can approximate the length of this chord if we know the length of this arc. Alright? So I'm going to say that the chord length, that part in yellow, is the same as delta x. Okay, so what we see here is that I have actually two isosceles triangles. This big triangle right here is isosceles because remember that these two sides are radii and all radii are congruent, so I have two equal sides. And then I also have another isosceles triangle right here. So remember that V1 and V2 are congruent because they have the same magnitude, just different directions. I have an isosceles triangle here. So I'm going to draw those on the next page. Actually, I might already have them drawn. Oh yeah, they're right there. Just going to rename this delta x. Okay, so my base for the larger triangle is delta x. And I have these two sides that are congruent. Oh, and these are not. Okay. And then I have, on the second triangle, my base is delta v, and v1 and v2 are congruent. Okay. And I also know that the angle in the larger triangle between the two congruent sides is theta. I have that marked right there for you. Okay, so I want to see if I can relate these two. If I can prove that these two triangles are similar, then I can set up some interesting equations. So all I need to do is to figure out a way that I can prove that this angle here is congruent to this angle here. And then I can prove they're congruent by side angle side for congruency. Okay, so how I can get that is if I extend. Now it's going to get a little crazy with the diagram, but that's okay. Alright. If I extend this line, this was the line for V1. And I extend this line, this is the line for V2. What I have there is a kite. Okay? And I know that this angle right here is the same as 180 minus theta. A pair of opposite angles in kites are always supplementary. So I know that this angle right here is 180 minus theta. I'm just going to draw an arrow. This is 180 minus theta. Okay. Now what I can say next is, well, these two lines, I'm going to extend again. It's going to get a little crazy. This line here is parallel to this line here. And that's because, remember that this green line was just me shifting V1 down. So they have the same direction, it's just moved down. So they're parallel lines, okay? So this is parallel. And I know that this angle right here is 180 minus theta. And I want to compare it to this angle here, because this angle here is inside the triangle I'm looking for. Well, they are same side interior angles. And what we know about those is that those are supplementary. They have to add to 180, meaning that this angle, put it in purple, is actually just theta. This is theta. Alright? So 180 minus theta plus theta gives me 180, so they're supplementary. So now I know that this angle right here is theta, and the triangles are similar. So from here I can write a similarity statement. I can say that R over delta x is equal to V1 and V2 are the same, so I'm just going to call it V over delta V. Okay, so I'm comparing this over this equals this over that. Alright, I'm going to cross multiply. So delta V times R is equal to V times delta x. Alright, I also know at this point that delta x is equal to v times t, if we're talking about average velocity, or velocity isn't changing, like the magnitude of velocity isn't changing, so we can use this equation. I'm going to plug that in. Delta v times r is equal to v times vt. Alright. And then so from here I can write a similarity statement because these are similar triangles. So I can say that R over delta x is equal to V1, but really V1 and V2 are equals. I'm just going to call it V over delta V. So I'm saying that this over this is equal to this over that. Alright. Now I'm going to cross multiply. So I get R times delta V is equal to V times delta x. Alright. Recall that if the magnitude of velocity isn't changing, delta x is simply v times t. So if we're talking about average velocity, or if magnitude of velocity isn't changing, we can get distance by just v times t, okay? Or rather, v times delta t. All right. Just to erase that to be a little more specific. So I'm going to plug this statement in, this part right here, and for delta x down here. So I get r times delta v is equal to v times delta t. Simplify, I get r times delta v is equal to v squared times delta t. Now I'm going to divide by delta t and divide by r, just rearrange a little bit, and I get that delta v over delta t is equal to v squared over r. And remember that acceleration is change in velocity over change in time, so this is equal to centripetal acceleration. Alright, so our equation for centripetal acceleration is v squared over r. Alright. Now finding centripetal force is actually pretty simple. We know that force is equal to mass times acceleration. So centripetal force is equal to mass times centripetal acceleration, which is this right here. So it's mass times v squared over r. So these are two very important formulas. This one right here and this one right here. Okay. Another way you might see these formulas is in terms of angular velocity. So recall that in circular motion, linear speed is equal to radial distance times angular velocity. Alright, so occasionally what they'll do is plug in for v as r times omega. I can rewrite this as AC is equal to r times omega squared all over r, and I get that AC is equal to r squared times omega squared over r. So AC is equal to r times omega squared. And then the final step here is to recall that angular speed is equal to radians over time. So I can rewrite this as AC is equal to r times 2 pi over t all squared. Okay, remember that there are 2 pi radians in a circle, and then angular speed is just radians over some unit of time. So I can simplify that down to AC is equal to 4 pi squared r over t squared. Now if you want to write your force in terms of this, I just now plug in this long thing in for acceleration right here. And I can write force in terms of time. For pi squared r over t squared. Okay, so this is kind of a lot to look at, but really try to focus on these two if you can, understanding those, and in the next video we'll look at solving some problems.